Welcome back! In our previous lesson, we covered the fundamentals of the polar coordinate system and how to convert between polar and Cartesian coordinates. Today, we are taking the next step, applying calculus in polar form. Together, we'll learn how to find tangent lines, compute areas, and calculate arc lengths. If you enjoy clear, step-by-step math explanations, don't forget to subscribe, hit the like button, and share this video. Your support helps our channel grow and keeps us creating quality content. Thank you. Let's begin with a quick review. In polar coordinates, any point in the plane is described by two values: r, the distance from the origin, and theta, the angle measured from the positive x-axis. The relation between polar coordinates r and theta and rectangular coordinates x and y is given by the following equations. Sometimes polar coordinates are much more convenient than Cartesian, especially for curves with circular or spiral symmetry. With this in mind, let's see how calculus works in this setting. First, let's talk about tangent lines. In Cartesian coordinates, we use dy dx, but in polar coordinates, we can't just derive r with respect to theta because we need to take derivatives with respect to theta. From our work in the previous video, we have the following set of conversion equations for going from polar coordinates to Cartesian coordinates. Now we will use the fact that r is a function of theta. R equals f of theta. Substituting this into set of conversion equations gives the following set of parametric equations with theta as the parameter for the curve. The slope of the tangent line is given by dy dx. We treat our conversion equations as parametric equations, where theta is the parameter. Then we find the derivative of y and x with respect to theta. We may use the product rule for derivatives to calculate each derivative. After that, we divide them to obtain the slope in polar form. Consider a curve given in polar form r equals f of theta, and taking theta as a parameter, we can write its parametric equations as x equals r times cosine of theta and y equals r times sine of theta. Then the slope of the tangent line to the graph of r equals f of theta at the point r and theta is given as follows. This formula comes from converting x equals r times cosine of theta and y equals r times sine of theta into derivatives. Consider the polar equation r of theta is equal to 1 plus sine of theta. Find the tangent line at theta is equal to pi over 3. Let's do it step by step. Step 1. Differentiate r with respect to theta. dr d theta is equal to cosine of theta. Step 2. Divide dy dx to get the slope of the tangent line. Use the equation above and replace theta with pi over 3. Step 3. Convert the polar curve r is equal to f of theta into parametric equations, using theta as the parameter. X equals f of theta times cosine of theta, and y is equal to f of theta sine of theta. Express the polar equation. R is equal to f of theta as a parametric curve. Step 4. Substitute the specific value of theta into the parametric equations to find the corresponding x and y coordinates. Find the point on the curve by substituting theta for pi over 3 in the parametric equations. Step 5. Once you have the slope and the point x and y, use the point-slope form to write the equation of the tangent line. Now, let's bring it all together. Take the slope you calculated earlier and the point x and y you identified. Plug these values into the point-slope form of a line. This will give you the precise equation for the tangent line you are looking for. The following image shows the graph of the polar equation and the tangent line at the specified point. Now that you understand how to find tangent lines in polar coordinates, let's analyze two important cases: when the tangent line is horizontal and when it is vertical. See the formula for finding the tangent line in polar coordinates, and then the conditions for each type of tangent will become clear. A horizontal tangent occurs when the slope is 0. This happens when the numerator is equal to 0 and the denominator is not 0. So you must solve the equation. A vertical tangent occurs when the slope is undefined. This happens when the denominator is equal to 0 and the numerator is not 0. So you must solve the equation. To make things more concrete, let's study one of the most famous polar curves, the cardioid, given by the equation. I'm using this example because some calculations have already been done, so we'll save time. A horizontal tangent occurs when the y theta is equal to 0. Taking the calculations already done in the previous example, we just have to solve the trigonometric equation. Notice that cosine of theta is a common factor in both terms. Factor it out. The zero product property states that if the product of two or more factors is 0, then at least one of the factors must be 0. This gives us two separate simpler equations to solve. Solve each equation for theta. Find the values of theta for which cosine of theta is equal to 0. On the unit circle, the cosine value is the x-coordinate. The x-coordinate is 0 at the top and bottom of the circle. Theta is equal to pi over 2 and theta is equal to 3 pi over 2. To solve the second equation, isolate sine of theta. Now find the values of theta for which sine of theta is equal to minus half. On the unit circle, the sine value is the y-coordinate. The y-coordinate is minus 1/2 in quadrant 3 and 4. Theta is equal to 7 pi over 6, and theta is equal to 11 pi over 6. A vertical tangent occurs when dx dy is equal to 0. Taking the calculations already done in the previous example, we just have to solve the trigonometric equation. This quadratic in sine of theta can be solved to give the values of theta where vertical tangents occur. Find the values of theta for which sine of theta is equal to -1. The y-coordinate is -1 at the bottom of the circle. Theta is equal to 3 pi over 2. And find the values of theta for which sine of theta is equal to 1/2. The y-coordinate is -1/2 in quadrants 1 and 2. Theta is equal to pi over 6, and theta is equal to 5 pi over 6. We need to obtain the corresponding x and y coordinates to obtain the horizontal and vertical tangent lines. Substitute the specific value of theta into the parametric equations to find the corresponding x and y coordinates. After that, in the graph below, we will mark the exact points where the horizontal and vertical tangents occur. Note that both the derivatives dy d theta and dx d theta are 0 when theta is equal to 3 pi over 2. Using this information alone, you don't know whether the graph has a horizontal or vertical tangent line at the pole. We know that at this point, the curve passes through the origin. This is a specific case of a general theorem about tangents of polar curves. Let the polar curve be defined by the equation r equals f of theta. We are given that the curve passes through the origin at theta is equal to theta 0, which means r of theta 0 is equal to 0. We now find the slope of the tangent line, that is, the derivatives of x and y with respect to theta 0. We know that at theta is equal to theta 0, the curve passes through the origin. So f of theta 0 is equal to 0. Let's substitute this into the expression for dy dx. We can cancel out f prime, and we obtain that the slope of the tangent line at the origin is tangent of theta 0. However, tangent of theta 0 is also the slope of the line. Theta is equal to theta 0. So we can conclude that this line is tangent to the curve at the origin. Thus, we have established the following result. Let the polar curve be defined by the equation r is equal to f of theta. If r of theta 0 is equal to 0, then the polar curve passes through the origin at theta is equal to theta 0, and the line theta is equal to theta 0 is tangent to the curve at the origin. Since at 3 pi over 2 the curve passes through the origin, then the slope is the tangent of 3 pi over 2, which is infinity. Thus, there is a vertical tangent line at the pole. Next, let's find the area of a region defined in polar form. If r is equal to f of theta is a continuum function, then the area bounded by the graph of the polar curve between the radial lines theta equals alpha and theta equals beta is equal to. Why does this work? We need to use the formula for the area of a sector of a circle. Consider the area enclosed by the polar curve defined by the equation r equals f of theta and the rays theta equals alpha and theta equals beta. To find the area of this region, partition the interval alpha beta into n equal subintervals delta theta. On each subinterval, we approximate the curve with the circular arc r is equal to f of theta. We have now pi-shaped sectors along each part of the domain. The area of each small sector is given by the formula. Then approximate the area of the region by the sum of the areas of the n sectors, as shown below. The limit of the Riemann sum is a definite integral. Let us see how it works. This example is a direct application of the formula. This type of equation represents a special family of polar curves called spirals. A spiral is a curve that wraps around a central point. Some of the most common types of spirals are shown below. Archimedean spiral, parabolic spiral, logarithmic spiral, littus spiral, and hyperbolic spiral. Therefore, we need to find the area of an Archimedean spiral. To find the area enclosed by this equation, we use the formula above. In this problem, the bounds are theta equals 0 and beta equals 2 pi. Substitute the given function and bounds into the formula and simplify the integrand. Evaluate the integral using the power rule for integration. After that, apply the limits of integration from 0 to 2 pi. Evaluate the expression at the upper limit and subtract its value at the lower limit. Perform the final multiplication to get the area. Let's look at another example. Let's dive into another type of polar curve family, rose curves. These curves create beautiful flower-like shapes and they are defined by the equations r equals a cosine of n theta or r equals a times sine of n theta, where a is a non-zero constant and n is an integer. The number of petals on the rose curve depends entirely on the value of n. If n is odd, the curve has exactly n petals. If n is even, the curve has 2n petals. For example, r equals a cosine of 3 theta has 3 petals, since n equals 3, which is odd, while r equals a sine of 2 theta has 4 petals, since n equals 2, which is even. To find the area of a single petal, we need to determine the correct integration limits. If we use the range from 0 to pi as our limits, we'll calculate the area of the entire curve, all 3 petals, not just one. To avoid this, we'll sketch the graph. Plotting the curve helps us identify the specific start and end points of a single petal, giving us the correct integration limits. This ensures we calculate only the area of one petal as requested. We can find the integration limits by understanding how the rose curve is formed from the sine function. Let's look at the equation r is equal to sine of 3 theta and its Cartesian graph. The first petal is traced as the radius r goes from 0 to its maximum value and back to 0. This occurs as theta sweeps through a specific range. When theta equals 0, r equals sine of 0 equals 0. The maximum value of the sine function is 1. This happens when 3 theta equals pi over 2, which means theta equals pi over 6. Here, r is at its maximum length. The function returns to 0 when 3 theta equals pi, which means theta equals pi over 3. So, as theta increases from 0 to pi over 3, the radius r grows from 0 to 1 and then shrinks back to 0. This single sweep traces out one complete petal. Therefore, the integration limits for finding the area of one petal are 0 and pi over 3. To solve the definite integral, we will use a power reduction formula for sine. We can extract the constant 1/2 from the integral and integrate term by term. The integral of 1 with respect to theta is theta. The integral of cosine of 6 theta with respect to theta is sine of 6 theta over 6. Now we evaluate the expression at the upper bound, pi over 3, and the lower bound, theta equals 0, and then subtract the two results. Since sine of 2 pi equals 0, this greatly simplifies the final calculation. Finally, we multiply by the constant that was outside the integral. I will complete the graph so you can understand how the 3 petals are formed. Let's look at another example. Let's introduce a fascinating family of curves in polar coordinates called limaçons. A limaçon is defined by an equation of the form r equals to a plus b cosine of theta, or r is equal to a plus b sine of theta, where a and b are real constants. Depending on the ratio between a and b, the limaçon can take on very different shapes. When the absolute value of a is less than the absolute value of b, the curve has an inner loop. When the absolute value of a is equal to the absolute value of b, the curve becomes a cardioid, a heart-shaped curve. When the absolute value of A is greater than the absolute value of B, the curve is a dimpled or convex limmason without an inner loop. To find the area of the smaller loop, we must choose the correct limits of integration. If we integrate from 0 to 2 pi, we get the entire curve, not just the loop. To avoid this, we first sketch the curve in Cartesian coordinates, identify where the loop lies, and then set the appropriate limits. To graph this function, we must mark the values of theta where the curve passes through the origin, and the values of theta where r assumes an extreme value. We begin by setting the equation equal to 0 and solving the following trigonometric equation. The values of theta where the curve passes through the origin are 2 pi over 3 and 4 pi over 3, and the values of theta where r assumes an extreme value are 0 and 2 pi. We can see that as theta increases from 0 to pi over 2, r decreases from 3 to 1. As theta increases from pi over 2 to 2 pi over 3, r decreases from 1 to 0. As theta increases from 2 pi over 3 to pi, r increases from 0 to 1. As theta increases from pi to 4 pi over 3, r decreases from 1 to 0. Thus, as theta increases from 2 pi over 3 to 4 pi over 3, the radius r increases from 0 to 1 and then decreases back to 0. The smaller loop is traced out as theta increases from 2 pi over 3 to 4 pi over 3. Therefore, the limits of integration to find the area of the smaller loop are 2 pi over 3 and 4 pi over 3. To solve this integral, we use the half angle or power reduction identity to simplify the cosine squared term in the integrand. Integrate the resulting expression termwise and evaluate at the bounds. Finally, I will complete the graph so you can understand how the limmason is formed. Let's look at another example. We will present a family of well-known curves called circles. Equations of circles passing through the origin are among the simplest polar equations. These circles are tangent to one of the axes, and the equations are defined by the equations r is equal to a cosine of theta, or r is equal to a sine of theta, where a is a non-zero constant. In our problem, we noticed two intersection points. Setting the equations equal gives theta equals to pi over 6 and theta equals to 5 pi over 6. To find the desired area, we subtract the cardioid's area from the circle's area over these limits. We end this video with arc length in polar coordinates. Recall that the arc length of a parametric curve x equals x of t and y equals to y of t is given by a standard formula. To adapt this to polar form, we write x equals f of theta times cosine of theta and y equals f of theta times sine of theta for theta from alpha to beta. Differentiating with respect to theta and applying the product rule, we substitute into the arc length formula. After simplifying with the Pythagorean identity, we obtain the polar arc length formula. Arc length in polar form. If r equals f of theta is a continuous function, then the arc length L from theta equals alpha to theta equals beta is equal to Let's give 3 examples of this. Find the length of r equals theta for theta from 0 to 1. To find the length of the polar curve, we use the polar arc length formula. Substitute r equals theta and differentiate with respect to theta. To calculate the integral, we'll need to use trigonometric substitution here. Let theta equals tangent of theta. We know that the derivative of the tangent is the secant squared. We also need to swap the limits of integration. If tangent of theta equals 0, then theta equals 0. And if tangent of theta equals 1, then theta equals pi over 4. Substitute 1 plus tangent squared for the trigonometric identity of the secant squared. To solve this, we use integration by parts. I will leave 2 more examples for you to solve on your own, then check out the step-by-step solution.